Thank you to all the organizers for this opportunity to share my work with you, but also thank you for all the efforts organizing this webinar that I'm sure it will be great. So today I will speak about nanothermometry of plasmonic systems. So let me start by some context on what is why should we measure the temperature in plasmonics. So you know that nanostructured metals can be thought as nanoantennas because they can collect the energy of light very efficiently and confine that energy into the nanoscale. And how is that energy provided in the nanoscale? Well, it's mainly in three ways. It's in the energy of whole electron pairs, in electromagnetic field, and in heat. And all these phenomena is simultaneously present. And this has given rise to many, many applications in the field of plasmonics. And in some applications, the heat is the main reason why we use plasmonic nanoparticles, such as in photothermal therapies. In some other applications, people exploit the enhancement of the electromagnetic field, such in the case of CERS. And in this application, heat is actually a side effect, it's a problem that you would like to avoid. And there are some other applications, such as plasmonic photochemistry, where we don't really know the role of heat. And what all these applications have in common is the necessity of reliable and quantitative measurement of the temperature. However, while it is very straightforward and it's very easy to hit with plasmonic nanoparticles, it is very hard and very challenging to know exactly how much we are hitting. Why is that? Why is it that hard to measure? Well, there are many reasons. One of the reasons is that the temperature is very confined in a very small area around the nanoparticle. So, for example, here we can see an example of 60 nanometer gold sphere, and we can see that the temperature decays in 50 nanometers. So if you want to use a technique based in light, we have the diffraction limit of light. And here you have a picture that is drawn to scale. And we can see that if we use light, we will be averaging hot and cold areas because the size, the minimum size of the diffraction limit is much larger than the temperature size. And also it's very hard to control in the nanoscale because we know that a small change in the geometry of the particle can cause a very large effect on the absorption cross-section of that particle. So how are we going to approach this complexity? Well, our approach will be to study and measure temperature at the single particle level. And what do we need for that? We need two things. We need a technique, a fabrication technique to isolate single particles, and then we need a thermometer that works also at the single particle level. So these two things is what I'm going to introduce now. First, how do we create arrays of single particles? Well, you know that chemists are very skillful and they can synthesize many nanoparticles of different material, different shapes in flasks. But then how do we put them into a substrate to study them at the single particle level? Well, I'm going to present a technique based on optical forces to do that. How? Well, we have a substrate here, put a drop of colloidal particles, then we have a laser beam that we focus on the sample, and hopefully you can see here a video. This is a dark field video. That green shiny spot there is a laser, and hopefully you can see some colloidal nanoparticles moving freely in Brownian motion. And when one of them crosses the focus of the beam, it feels an optical force and it gets printed onto the substrate. And then we move the substrate to a new position, and we have all the coordinates for the particle loaded on the computer. All the process is automated, and at the end of the day, what we can have is all these patterns, complex patterns on glass, such as a map or a workup. So with this technique, we can create arrays of isolated single gold nanoparticles or single particles in glass. Well, now that I've shown this, I need to go to the second method, which is a thermometry that works at the single particle level. And this method is called Anti-Stokes thermometry. It wasn't my idea or our idea. This was inspired on this excellent papers, and many of these papers belong to the groups of the organizers of this webinar. So I also thank them for the inspiration. Okay, so what we need to quantify is what is called the photothermal effect. It's very simple to understand. We have a nanoparticle, we have light, incoming light, and then the temperature of the particle increases. And in many cases, this temperature increase is linear with the irradiance, the excitation irradiance. And I'm sure you will agree with me that all we need to characterize the system is this response is linear, is the slope of this linear trend. So that slope is what we call the photothermal coefficient, beta. So starting at this point, I will refer to the photothermal coefficient many times. Pay attention, is this, is the slope of the temperature increase versus the irradiance. Okay, so this technique is based on a phenomenon called photoluminescence emission. So here I have an example. Imagine a single gold nanoparticle is illuminated at the plasmon resonance at 532. And we can see that the particle emits light at different wavelengths from the excitation. And that here you see an example of the emission photoluminescence spectrum. And you can see that some of the spectrum is what is called the Stokes spectrum. This is at larger wavelengths. That means lower energies. And some part of the spectrum is what is called the Anti-Stokes, which is a shorter wavelength. That means higher energy than the excitation. But if the Anti-Stokes has higher energy than the excitation, that it means that that energy must come from energy that was thermally available on the nanoparticle. So if we are smart enough to analyze this Anti-Stokes emission, it carries information about the temperature of the particle. And what is also very useful is that the Stokes part carries information about the excitation irradiance because it's linear with the excitation irradiance. So all the information that we need for this plot that I said before for the thermal effect is here. So from the Anti-Stokes, we will get information on the temperature, and from the Stokes, we will get information on the irradiance. Okay, how do we get this information? Well, let me go to the next. Yes. So what we do is we use the same laser to hit and to excite the photoluminescence. And then we do a raster scanning of the nanoparticle through the beam, through the focus of our beam. So at the end of the day, we have this hyperspectral image. At each pixel, we have the photoluminescent spectra. So then we analyze that, and what we have is this, is the photoluminescent spectra taken at many different excitation irradiances, and for each irradiance, it will correspond to a different temperature. Okay, and then for the Anti-Stokes, we have this modeling. We say that it's proportional to the excitation irradiance, that is proportional to the some function, which that shape will be like an intrinsic property of the particle, and then it will be proportional to the distribution of states, which usually we use a Bose-Einstein distribution. But of course, in order to extract the temperature here, we will need to know what this function is. But since we don't know it, what we do is we calculate ratios between two different spectra. And when we calculate the ratios between two spectra, this factor gets canceled out, and all we have left is the ratio between the Bose-Einstein distribution. And then we have another hypothesis, which is the one that I said before, that is that the temperature increases linearly with the intensity. And then we get this expression that might look complicated, but it actually has a single free parameter, that is the photothermal coefficient. Okay. Then we calculated, so we have this, we calculate all the ratios, and we fit to each one of the ratios, we extract one beta, and at the end of the day, we have this, the temperature versus the irradiance. So if you was lost on all this discussion, the take-away message, the take-home message is that from a single hyperspectral image, we extract the photothermal coefficient. So what I have presented so far is what we call hyperspectral anti-Stokes thermometry. It's a thermometry that works at the single particle level. We extract the photothermal coefficient beta from a hyperspectral photoluminescent image. It's an in situ and it's label-free measurement. We haven't used any probe. We haven't added anything to the particle. It does not require any previous information on the nanoparticle or the surrounding media. It can be implemented with a single laser at constant power, and the photoluminescence is emitted from the nanoparticle, so there is no aberration artifact of cold and hot areas, because the temperature of the plasmonic component is extracted. Good. So far I presented the methods. Now I'm going to use this method to study a system of bimetallic particles made of gold and palladium. And why I'm going to study this system? Well, you know that there is a field called plasmon-assisted chemistry, and this field aims to exploit the properties of plasmonic particles for a chemical reaction. As I said before, a plasmonic nanoparticle can be thought as a nano source of hot electrons, as a source of electromagnetic field, and a source of heat. And all this phenomenon can be exploited for chemical reaction. And in particular, the temperature is very relevant due to the Arrhenius law, because we know that reaction rates have an exponential dependent on the temperature. So in this field of plasmon-assisted chemistry, it's very important to precisely know the temperature of the system. And why I'm going to study gold-palladium system? Well, gold nanoparticles are very useful for their plasmonic properties, but if you want to use them for chemical reaction, they are not so catalytic active. So in order to enhance their performance, they are usually combined with the catalytic material. So that's why it is interesting to study gold-palladium composites. But as soon as you have a composite, their thermal response can be very different from the thermal properties of the isolated counterparts. We synthesize core shell nanoparticles, gold and palladium. We have these three systems. First, the naked gold particle, and then two core shells with two different thickness of the palladium shell. One has 2 nanometer thickness, and the other one has a thickness of 4 nanometer. We use optical printing, and we created these arrays of isolated particles. We measure the optical properties of these particles at the single particle level, and something that we observed was that here, for example, I don't know if you can see my pointer. You can see my mouse. Well, it doesn't matter. So for example, here I am showing the photoluminescent emission of these three systems, and what we can see is that for the core shells, the spectrum is broader, and also the emission quantum yield of photoluminescence is lower. And this is something that is, I think, is well understood, because as soon as you have a damped oscillator, which in this case will be the plasmon resonance, and you include some damping to the system, which in this case will be damping by the palladium shell, it is a well-known effect that you have a lower quality factor. Okay. So then we use the thermometry, as I explained before, and what we found was that the photothermal coefficient of the core shells was lower than the one of the naked gold. Okay, so then we wanted to understand a bit more on the relationship between the interface and the photothermal response of the particles. So we designed these systems. We prepare two systems that had exactly the same amount of gold and palladium, but with a different interface. So in one case, we had a 2 nanometer continuous shell. And in the other case was exactly the same amount of palladium, but instead in small satellites. So in this way, the interface between both materials is minimized. And we found something quite interesting, that was that the naked gold and the gold with the satellites had almost the same photothermal response that was then damped by the core shell system. So this means that the interface is the key aspect defining the photothermal response of the particle, because the damping of the resonance is done happens at the interface. So as a conclusion of this part, we can say that this is an example of the temperature increase for all the systems. We can conclude that a thin shell of 2 nanometers of palladium can have a large effect in the photothermal coefficient of core shell nanoparticles, because it can reduce it up to 40%. And then 2 systems with the same materials in composition and quantity can have very different thermal behaviors according to the spatial distribution of its constituents. Because the inclusion of palladium affects the photothermal coefficient mainly by altering their absorption cross-section due to plasmon damping. Good. Then one last experiment that I want to share with you is that we perform a thermometry comparison. So as far as I know, anti-Stokes thermometry hasn't been compared or validated with another method. So we started a collaboration with Guillaume Bafou, and we compare anti-Stokes thermometry with another thermometry method that is called cross-grating wavefront microscopy. I'm not going to explain how it works because he will be presenting in 2 weeks in this webinar. So hopefully he will explain it. But the idea is that you can acquire 2D temperature maps that are diffraction limited. So this comparison, we didn't do it at the single particle level. Instead, we did it at the array level. We created these arrays of gold disks. They were like 40 by 40 in size. We used an illumination beam of 18 micron. That means that we were illuminated almost 500 particles simultaneously. We created arrays with 3 different disk size, and we use again a red beam at 640 nanometers to hit and to probe. And these are the results that we got with the wavefront microscopy. Here in the white box is where the array was, and then you can see this small circle in the center is the area that we use for the anti-Stokes measurements. So we compare the temperature inside that area with the 2 techniques. And well, we did the photothermal measurement in the same way that I described before. We can see that the photothermal coefficient that we got were like 1 order of magnitude larger than what we got for single particles. So this demonstrates that there was like a collective heating effect. And the main result is that we compare both techniques with a remarkable agreement. So here you can see in the dots are the result that we got from the anti-Stokes thermometry, and the solid lines is what we obtained with wavefront microscopy. And this good agreement also enhances the confidence in the anti-Stokes thermometry for the single particle level, where a comparison with alternative techniques is more challenging. So we're very happy about that. So you know that science is a teamwork, so I want to thank all the authors, in particular to Simone Snam and Mariano Varela. They are the first authors of 2 of the papers that I presented here. This work was mainly done at LMU in Germany, but also at CBOL in Argentina, because I had a DAD fellowship and I was traveling back and forth between both labs, in the labs of Emiliano Cortés and Stefan Mayer, Fernando Stefani, and Janina Violi. And I want to finish by telling you that now we are starting a new group in nanophotonics in Argentina. I want to show you like where we are. We are here in Argentina, in the outskirts of Buenos Aires. There is this new building that was inaugurated like a few months ago. So we installed the optical tables also a few 2-3 months ago. Everything is brand new. And if you are ever nearby, please visit us in our new lab in Argentina. So thank you so much.
Thank you very much for your nice talk. It is good to see a lot of level 3 temperature measurements with a complex particle. So we already have 2 questions. First question from Kostas Kanopoulos. So he asked, what's the laser needed for generating strong enough force to clamp the particles?
Okay, so optical forces, when you have particles that are below 1 micron, are quite weak. But in this case, we have gold particles that have plasmon resonances, and the plasmon resonance enhance the forces as well. So in this particular case, when we use 60 nanometer gold particles, typically we have like 1 milliwatt focus to the diffraction limit of light. So that's like in a focus of 300 nanometer, we have like 1 milliwatts, order of magnitude.
Okay, we have a second question from Professor Klaus Kroy. I think you can directly ask also.
Klaus, do you want to ask it?
Okay.
We can read it.
It was a comment.
Yeah.
It was a comment
Yes.
just for your convenience, of course. If you can suspend your particles in a liquid solvent and you can heat them at the same time, then you can, of course, measure their hot Brownian motion, and you can compare the surface tension measured by your method with the surface tension deduced from the hot Brownian motion, and they should be the same if everything goes right, of course. So you have an independent check if this is possible for you technically. That was the point.
That will be a very nice experiment to do. I will be very happy to do it. It's also interesting that which temperature are we referring to? Because of course we have like the particle and we have the surrounding media, and we have the one thing is the temperature of the gold, and a different thing is the temperature of the solvent around. So we should like check exactly which temperature are we referring to, because also there are something called the interfacial resistance, interfacial thermal resistance, which creates like a temperature
jump,
exactly. So maybe the temperature inside the particle is not exactly the same as the temperature outside the particle. Yeah,
exactly. So the hot Brownian motion technique would give you the limit of from the outside, from the solvent, and the Kapitsa resistance would not be relevant for this measurement. But of course, for your measurement, it's a different thing. So if you are really accurate, maybe you can see the Kapitsa resistance.
Exactly. Yes.
Yeah. But that would be quite hard, I guess, because it's the Kapitsa resistances are not that big, right? They are small effects. Yeah. Usually. Yeah.
I don't know if I mean, yes, it's a small effect, but maybe there is a difference of a few degrees in like the inside and the outside.
Would be nice.
So, yeah, it would be very fun to do such an experiment. Yeah.
Okay, we have a question from Ode Barbara. Shouldn't you photothermal coefficient beta equal the absorption cross-section of the gold nanoparticle?
Yeah, yes. So in the photothermal coefficient, we have information about 2 phenomena: the absorption cross-section, but also the heat dissipation properties of the nanoparticle and the environment. So for example, the same particle on different media, let's say, it will dissipate heat differently, so it will have a different photothermal coefficient. So it's like, yeah, it's the convolution of the information of the absorption and the heat dissipation.
Okay, is there any further question?
Hi, Julian. Nice talk. I want to ask an additional question, adding to what Klaus said. So, as far as I saw, there was no indication for a Kapitsa resistance if you compare the wavefront sensing and the Anti-Stokes measurement, right? Because the wavefront setting is probing the environment, and the Anti-Stokes is not. Right? Was I wrong?
No, you're right. You're right. So here, yeah, one thing is that in this experiment, we were on the collective heating regime, which means that the temperature was homogeneous over a scale of several microns. But still, you're right, we are measuring the temperature of the emitter of photoluminescence. That means the temperature of the gold. It should be like the inner temperature. So yes, you're right, we didn't see any like huge difference between both methods, indicating that in this case, the resistance was not that large. So these particles, in this case, these disks were fabricated by EBL lithography. I think that the capacitor resistance is larger when you have colloidal particle coated with molecules. So, but yes.
I mean, if I may ask a second question, I saw in one of your drawings that you assumed a capacitor resistance or temperature jump between the palladium and the gold core, or wasn't that, or at least in the drawing it was like this, and probably you would expect a capacitor resistant effectively rather for solid-solid interfaces rather than for solid-liquid interfaces, or would you expect something between palladium and gold, or?
Okay, yes, good question. So maybe I have some slide on that. Yes, so actually one question that you may ask is, okay, you are measuring the temperature of your core shell particle, but which temperature are you measuring? Are you measuring the gold, the palladium, an average, or whatever? And I think that in this case, because these are two metals, they are highly conductive. So all the modeling that we did says that the temperature is quite the same on both materials. Maybe I have another one. So one, I think I have it here.
Yeah.
Yeah, exactly. So this is the simulation that we have, and what we can see that the temperature is almost the same in gold and in palladium. And there is a small drop that, of course, is proportional to the capacitor resistance between gold and palladium. But here we have this issue that all these thermal properties are not very well measured. I mean, are not available in the literature. If you want to search for what is the capacitor resistance between these, gold and palladium, it's very hard to be quantitative and to predict. That's why I think it's important to develop this kind of experimental method to measure. Because at the end of the day, you cannot trust your calculation because you don't really know exactly what will be the capacitor resistance between your particle, the solvent, with the molecule that you're using to coat the particles. So, for example, here in this plot, you can see that our theory has a mean and a max. Can you see these two black lines? That the reason to have this mean and max is due to all the dispersity in the coefficients that we found in the papers. So when you want to get quantitative, it's very hard to do it.
But this is measured from different particles, so you get even a size dispersion or whatever.
No, I mean, the histograms that you see there, it's a dispersion because we have many particles. But the black solid lines is what our theory says it should be. And the reason why we have two lines, one that says mean and one that says max, is because in the literature, in the papers, all the coefficients that we need to put into the equations are not very well defined. So then if you want to be quantitative in the prediction, it's very hard because you don't know exactly your system. You don't know what to model. That's why I think it's very important to have experimental methods and to measure it.
I think we have a comment from Professor Croy. I think that's a comment, not a question, but
I can also say it, with computer simulations of Lennard-Jones fluids, you get huge capacitor resistances because the fluid, if you heat it, becomes very dilute. The Lennard-Jones fluid is not like water, right? It's different. It's more a bit more like a gas almost. So there you see huge Kapitsa resistances. But I think for instance, in a solvent like water, it is probably pretty hard to get such a strong effect, right? But maybe near the critical point, you could see such a thing. Yeah.
But is that then something like a Kapitsa resistant or a shell of a kind of gas-like shell with a different heat?
It's kind of the same, right? So in the Lennard-Jones, you just see a density dip around the particle, and that causes the resistance, and temperature cannot be transmitted very well, right? Of course, in the simulation we have no radiation, we have only convection, or collision of particles that transport the temperature, and in the experiment it's even more complicated because some of the heat is transmitted with radiation and some of it is convectively or conductively transmitted. But what I also heard from people who said Kapitsa resistances are normally small in most liquids. If you are not doing something really special with, I don't know, superconductivity or whatever, I think normally they are small and hard to measure. It's a challenge.
Yes. So if I'm allowed to say like a last comment, in this method, I'm using the strong hypothesis that the temperature is linear with the intensity. And that probably breaks in all these extreme situations that you are mentioning. So we should think about how to implement the method in these situations.
Okay, I think we are in time. So I would like to thank again all our speakers today. And
thank you.
Next week we will have a same time on the same day webinar. And I look forward to see you next week. So thank you very much again, everyone.